Hi everyone, today our group will present about self-healing concrete. As we know, concrete is the most popular material in construction. However, professional concrete can crack easily because of heavy, loose and bad winter. In line with SDG 9, our industry needs smart and more sustainable material. This is why we chose a self-healing concrete. This innovative material has special bacteria inside. When a crack form and water enter, the bacteria will wake up. It will react and produce calcium carbon to close the crack automatically. This help the structure last longer. Now, let's look at the problem statement. Traditional concrete has a few big problems. First, manual inspection and repair are very expensive and cost a lot of time. Second, if we ignore small crack, they will become bigger. Water will enter and cause the internal steel to rust, which make the structure dangerous. Lastly, making cement for repair create high carbon emission, which is bad for the environment. Therefore, we actually need a smart automatic material like self-healing concrete to solve this problem independently.
Now, let's look at how crystalline self-healing concrete actually works. Unlike conventional concrete, crystalline self-healing concrete contains special crystalline chemicals that are mixed into the concrete during production. When the concrete develops small cracks, water is able to enter these cracks. Instead of causing further damage, the water activates the crystalline chemicals that are already present inside the concrete. Once activated, these chemicals react with moisture and unhydrated cement particles. This chemical reaction produces insoluble crystals that begin to grow inside the cracks, pores, and tiny capillary channels. As the crystal continue to grow, they completely fill the empty spaces and block the pathways through which water can travel. This reduces water permeability and protects the steel reinforcement inside the concrete from corrosion. One important advantage of this technology that is the healing process is repeatable. Whenever new moisture enters another small crack, the remaining crystalline chemicals can react again, allowing the concrete to continue repairing itself throughout its service life. This self-healing mechanism significantly improves the durability and lifespan of concrete structures while reducing future maintenance requirements.
Hi, I'm Shabil and I will be explaining the innovation features and the 5 key resources involved in this smart material. Traditionally, concrete is a passive material. When it cracks, it stays cracked until we manually fix it. The breakthrough innovation here is transforming concrete into a smart active system. By using engineering principles of hydrophilic crystallization, the material gains the autonomous ability to sense water, ingress and heal itself from within, perfectly aligned with the technological advancement of IR 4.0, which is Industry Revolution. According to study by Roy Floss, this technology is exceptionally innovative because it can completely seal microcracks under 300 microns when constantly exposed to moisture. Therefore, this innovation is ideally applied in water retaining structures and underground engineering, such as water tanks, basements, tunnels, and marine foundations, where water contact is continuous. To successfully implement this technology, we rely on 5 critical resource pillars. First, people. It requires collaboration between material scientists to formulate the mixture and civil engineers to manage the structural applications. Second, material. The primary ingredient is the active chemical crystalline admixture mixed directly into the concrete batch. Third, equipment. No complex machinery is needed on site. It utilizes standard concrete batch mixers, making it highly practical. Fourth, technology. In research and development, advanced technology like scanning electron microscopy or SEM is used to analyze the needle-like crystal growth inside the concrete pores. And fifth, information. Our engineering baseline relies heavily on academic research and standard codes, such as the American Concrete Institute, specifically ACI 212.3R Chapter 15.
Okay, I will continue the presentation by explaining the benefit of crystalline-based self-healing concrete. The first benefit is that it can automatically seal small crack. When the water enters the concrete, the crystalline chemical react with the water and form crystal that can fill the crack. The second benefit is that it can reduce water leakage by making the concrete more waterproof. It also improves durability by protecting the concrete from the moisture and harmful chemical. Besides that, self-healing concrete reduces maintenance costs because of fewer repairs are needed. It also extends the service life of the structure, allowing it to last longer before the major repairs are required. Lastly, it is environmentally friendly because of reduced material waste and carbon emission from the repair work. Now, let's move on to the challenges. One challenge is that the healing process is quite slow and may take several days or even a week. It also requires moisture because the water is needed to activate the healing process. In addition, self-healing concrete is not suitable for large cracks, as this they require conventional repair method. Lastly, its performance depends on the environmental conditions such as temperature, humidity, and water availability. That's all from me.
Assalamualaikum. My name is Kamarun Najmi bin Shaman, student ID 2025 24 3704. I will now explain my part, which is mitigation with self-healing concrete. Number 1. Structural engineering addressing white cracks. Standard self-healing mechanism, autogenous or autonomous, are primarily designed for micro cracks. White cracks present a significant engineering challenge as they often exceed the capacity for traditional healing agents. Firstly, crack width control. To use structural design to limit the crack width, example, adequate reinforcement ratios, so that they fall within the self-healing range, typically 300 micrometers. Secondly, hybrid approach. Combine structural reinforcement with autonomous agents, which is micro-encapsulation or vascular system that can be triggered once the crack width is controlled. Thirdly, engineered cementitious composites, ECC. Integrate materials that promote multiple micro-cracking instead of a single large structural crack, making the damage more manageable for the healing mechanism. Number 2, operational excellence training batch plan workers. The, the effectiveness of self-healing concrete is highly sensitive to the mixing process. Improper handling can destroy capsules or render additive ineffective. Firstly, mixing precision. Educate on sensitivity of autonomous additive by ensuring microcapsules are not crushed during the mixing phase due to excessive shearing or aggregate size. Secondly, material compatibility. Emphasize that self-healing concrete is a specialized mix. Unauthorized water adjustment or chemical substitution will disrupt the chemical balance required for healing. Thirdly, quality control, QC. Train workers on identifying the proper distribution of admixture or capsules during the batching process to ensure structural consistency. Last but not least, strategic alignment. For Sustainable Development Goal 9, SDG 9. Self-healing concrete is a direct contributor to the United Nations SDG 9, which call for resilient infrastructure. Firstly, infrastructure durability. By increasing the service life of concrete structure, we reduce the need for frequent, resource-intensive repairs. Secondly, reduce carbon footprint. Extending the lifespan of bridges, tunnels, and buildings lowers the long-term demand for raw cement production, a significant source of global CO2 emission. Thirdly, economic sustainability. While initial costs may be higher, the reduction in maintenance and downtime for infrastructure leads to substantial long-term economic gains. Moving on to conclusion. Self-healing concrete is not just a technological novelty, it is a critical shift in civil engineering philosophy. By moving from a reactive maintenance model, fixing what is broken, to a proactive one, material that repairs itself, we can ensure safer, more durable, and sustainable infrastructure. Success requires the synthesis of intelligent structural design, rigorous training at the production level, and a long-term commitment to global sustainability goals.